just projectile thing. Except projectile thing and the relative motion are one part. Altogether, yes. That's a two-dimensional motion. That's what. I'm so nervous. Nervous? You know this stuff like your back of the hand, right? When is it going to be? I would like to have it on Monday, but I think it's a little too short, is it? Yeah. Let's take a vote. Who wants it on Monday? Yes. Yeah. Sometime next week but Monday. Any day but Monday. Huh? Any day but Monday. Any day but Monday, then I only have the choice of Thursday. Yeah.
It's just going to be on like free body diagrams.
Okay, let's do it on Monday, Thursday then. Okay. I sent an announcement on Canvas. Okay. I would like to change it, but I go by the.
And then we're gonna have another one next week.
I go by the popular.
Then we have another one next week too.
That's what I'm trying to build up to.
Oh.
So since chapter 4 is so long, is it, the one that we're going to have on Thursday is going to be on all of chapter 4?
Yeah. So it's going to be chapter 3 and 4, and then part of chapter 2 where vectors, find the resultant. Yeah, that is related to the lab that you did and the quiz I gave you last time. Okay. Oh, I'll have the quiz graded by Monday.
Oh.
I've been grading hell this week. Yes. That's what I thought.
Just give us all 10s and one more help.
That comes with the territory. All right, let's do this. Something like this I have given on a test. There's a lot of stuff on chapter 4, as Eric said, but what you really need to know is kind of fairly little, because if you can work out this kind of problems, that means you have learned the previous stuff. Previous stuff sections are to build you up to this, okay, these kind of problems. I'm going to work out a few problems on the board today. If you can master those, I think we are fairly well set for the test. You have a question? Yeah?
Yes. Are we going to have a homework assignment?
I already opened the homework assignments. I already signed them till on Thursday. But don't wait till Thursday. Start working them on weekend and then try to knock them out. Projectile motion problem is only, I think there are like 5 or 6 problems here. That's a very short assignment. But the other ones, Newton's second law is little involved, but that will help you do well on the test.
This is involved.
I think this has an issue with this problem.
Can I try this one?
Yeah, there's only 2 cables.
Can I try it?
Hmm?
So can I try it?
And now, only thing is this question is not complete. It says 3 cables, but they have only specified 1 left.
Well,
no,
are
one
we
with,
assuming?
with the left one 50 degrees below the horizontal and the right one 25 below the horizontal.
There's enough
Where
information.
is the third one?
The third one is the one that's hanging from the it's the resultant. The third one is the resultant.
The weight of the stoplight is 85 newtons.
Well, maybe it's like set up like that.
It's the third one is hanging from the
And it says below the horizontal. How can it stay like that? Below, it should be above the horizontal. unless there is another third string, you know. No, that's what I'm saying. This is not below the horizontal, this is above the horizontal.
Yeah, but that's because, like, say, if you were to draw it like this,
Yeah.
you have an angle right here, and you have another angle right there, like that. But if you go like this, these angles are the same.
Okay. All right. Yeah. I mean, it's not clear here. There's an example in the book. If you go with that, you know, to relate the book example to this, I put this thing here. You're right. I'll put this one. That will make sense what he's talking about. So this is what the situation is. One angle is whatever below the horizontal, the other angle is below the horizontal, and then the third one is straight down. You see that? Those are the three rows. Make sense? So with this, let's go back to the problem now. So there is an 85 Newton stop sign. That is the one hanging from the third rope straight down. Okay, and the weight of that stop sign is 85. And then there's one cable 50 degrees below the horizontal on the left, and the other one on the right is 25 below the horizontal. Make sense? So instead of the 37 is 50, instead of the 53 it's 25, is it? 25, and the weight of that stop sign is 85 newtons. So this angle is 50 here. This angle is 25, and the weight of this is 85 newtons. This is the weight. Now the question is find the tension in each table. That means tell me what is the tension here, here, and here. So since you haven't done a problem like this, take the tension in this cable to be T1 or T2, doesn't make a difference. Let's take this to be T1, this to be T2, this to be T3. Okay. And then you have to draw the free body diagram for this point. That not where all three meet. Okay. What would be the forces acting at that point? This is a string here, right? This is one end of the string, this is the other end of the string, okay? So there should be what in that string? Tension. What is the direction of the tension at this end? Should be to the middle of the string, right? What is the direction of the tension at this point? The middle of the string. So the T1 will be this way at that point, T1 will be this way at this point. Okay? And if you look at this string here, T2 will be down this way at this point, T2 will be up this way at this point. We are interested in only at this point, we don't care about it. And this will be T3, this is another string here, one end here, the other end here. T3 will be up here, T3 will be down. So you look at the free body diagram for this point. You can look at the free body diagram for this also. From that you can solve it. This basically what you have is three vectors for this point here. This will be just two vectors for this. Want me to work it out? Okay. I'm going to mark my tensions. T1, T2, T2, T3, and this angle is what, 50 degrees, right? And this angle is now, the first thing to do is, we are given the weight of this one. So that is mg is equal to 85 newtons. Keep in mind, a lot of students make this mistake. We are given the weight in newtons, they still will have 85 g. That is wrong, right? When would 85 g come into play? If the weight mass is given to be something, okay, then you multiply the mass by g to get the weight. Here they have already done that and given you the weight straight away. So do not multiply this by again a g. I mean, that is wrong. Alright, now I'm going to look at the free body diagram for this street sign. So this is what I have. I have the weight hanging downwards 85 newtons. And what else is here? Tension T3 upwards. And keep in mind, one special thing about this is nothing is moving, it is just hanging. Okay, this knot is not moving, the straight sign is not moving, the strings are not moving, they are just hanging. Okay. What is the acceleration of any of those points?
Zero.
Zero. It's not moving. Okay, it's not moving, therefore it is zero. Acceleration of this is zero, acceleration of not is zero, acceleration on any point on this string surface. So now I'm going to use Newton's second law for this object. What direction should I use?
Down.
Down, up doesn't make a difference. Okay? There's no point in using it horizontally. Understand that? Because there are no forces. You get zero is equal to zero. That's all. Okay? So I'm going to use Newton's second law. Because why did I use Newton's second law? Because I'm trying to find T3. I'm trying to find a force, right? Okay? That's why I'm using it. So let's use it downwards. Sigma F. First write the equation equal to MA. Alright, I have 85 newtons. My preferred direction is downwards. What would be the sign of 85 newtons? T3 is upwards, my preferred direction is downwards. What would be the sign of T3? Equal to mass. If you were to find the mass here, how would you find the mass of this street sign? Divide by G. 85 divided by 9.8. Okay, that is the mass. But we don't have to go that far, right? Why?
So
Acceleration is zero, the whole right hand side becomes zero. So this gives you what? Straight away you can find what? T3. Tension of the string, you can find that the string 3, you can find it. So in this one, although tension is a vector quantity, you do not have to give an arrow here because it depends what? Whether you are talking about the tension here or tension. You see that? At that point, tension is downwards, at this point, tension is upwards. So it depends on what point you are talking about, the tension will be different. It will be in opposite direction. So I found that is the first thing you want to attack. You want to get this free body diagram, from that you want to find T3 straight. Now you have two unknowns, because you already know T3, you have T1 and T2 unknowns, you need to find what those two are. Okay. Now I'm going to look at my dot here, that knot. So I have one force going here, T2, I have another force straight down, that is T3, and I have another force here, that is T. Let me draw the angles again. This angle will be 5 degrees. This angle, this is 90 degrees. Go straight. This is what I have. Three forces acting on a point, and what would be the acceleration of that point? Zero. When would the acceleration be zero?
If it's still or if it's moving.
That's right. Whether either it is stationary or it's moving at constant velocity. Okay. And for that to happen, what can you say about net force acting on that? Acceleration is zero. What can you say about the net force? Net force is zero. That's from here, right? Net force is on the left hand side. Now your acceleration is zero. That means right hand side is equal to zero. That means what? Net force is zero. Okay. So here the net force has to be zero because it's not moving up or down. Acceleration is zero. Okay. So net force is zero here. So that means what? Net force is zero means what? I can use that into two parts, right? I can split that into two parts. Net force in the horizontal direction should be equal to zero. Net force in the vertical direction should be equal to zero. If either one has any force component, you know what I mean? It will contribute to a net force. There cannot be any force in the y direction. There cannot be any net force in the x direction. That is a concept. Everybody understand that? Okay. Now, or else you can do this. You can use a component method. Do whatever you like. I'm going to use component method T1, T2, and T3 vectors. And I'm going to write the x component. T1 vector. What will be the x component of that T1 vector?
Yeah.
First of all, what do I have to worry about? When I mark my angles like this, what do I have to worry about? First thing.
What's negative and what's positive?
What is it negative or is it positive? Okay. I have this T1 vector like this. I want to find the x component. What direction is the x component pointed to? To my left, that is negative. You see that? Okay, so this is first thing I worry about is the sign. Otherwise, you can easily get into trouble. My sign is negative. How much is that? T1 cosine theta. What is my y component? What is the first thing I worry about? The sign of it. Is the y component from T1, is it positive or negative? Positive. What is the value? T1 sine. It is positive, so I'm not going to write the positive sign. T1 sine. That is because I'm looking at the acute angles between the vectors and the horizontal. Then the T2 vector. What is the horizontal component? Is it positive or negative? Positive. T2. Look at it like this. So the horizontal component will be pointing like this. Vertical component will be pointing like that. So there will be positive. What is the value? T2 cosine. What is the y component? Is it positive or negative? Positive. The value is T2 sine. If one is cosine, automatically the other has to be sine and vice versa. Only thing that can be different is one could be positive, one could be negative, both could be negative, both could be positive. Okay. And so that is done. Now T3. What is the x component of T3? Can I ask you? What is the x component of T3? T3 is acting vertically downwards. What's the horizontal component of a downward vector? That is not C. So I can put C. What is the y component of the T3 vector? Negative. Good. How much is that? We already found 85. If you want, you can write T3 or you can write 85 because we already found that. Okay. I'll write T3 and then I'll write it inside in parentheses 85 because we already found. from the free body diagram. Now, what is the next thing we do? We do the sigmas, isn't it? What is the sigma for this one? T2 cosine 25 minus T1 cosine 50, right? What is the sigma for this one? It will be T1 sine 50 plus T2 sine 25 minus T3. I'm going to substitute it. Now, that point is in equilibrium. What did I say? For it to be in equilibrium, what should happen to x component, net x component, and net y component? Net means the sigma part. This should be 0 and that should be 0. Okay. If this has any value, then it will never be resultant will never be 0. It will have some value. Okay. So this has to be 0 and that has to be 0. Alright. So the math is little involved here. So let's write this thing. Let me guess this. So I'm going to start with this guy. T2 cosine 25 minus T1 cosine 50. Do you know that this is a number? You can put it in a calculator and get a number. You can put this in calculator and get a number. So only unknown is T1 and T2. Okay? And then in this equation also there's unknown T1 and T2. Everything else you know. Okay? So you have two equations, two unknowns. So theoretically what can you do? You can solve for T1 and T2. Okay? That's the whole idea. So simultaneously. Alright, so from this I'm going to express T2 in terms of T1. I'm going to take this guy to the other side, which is T1 cosine 50. And then I divide it by cosine. That is my T. Why did I do that? So that I can come and substitute into this guy. This is for the x component. Similarly, I can write an equation for the y component, right? What should be the net value for the y component? It has to be 0 as well. Okay. If y component had any value, then you'll have a result. If x component had any value, you'll have a result. If x and y both have something, then you'll have a result. Only way that there is no resultant force means x has to be 0, y has to be 0. That is the only time you will get. What is the meaning of resultant? Resultant is the net force, right? All the forces added together and how you represent all the forces with one force. Okay? That's the meaning of net force. That is sigma f. Okay? This one we know there is no acceleration at this point. That means sigma f has to be 0. How can sigma f be 0? So sigma y has to be 0. Sigma x has to be 0. Without that, it can never be equal. Alright, so I'm going to write the next equation for y. That means T1 sine 50 plus T2 sine 25 minus 85. This has to be. Now I'm going to come and substitute for T2 in terms of T1. T1 sine 50 plus T1 cosine 50 divided by cosine 75 times cosine times sine 25 is equal to 8. I took 85. Now you'll see that I have only what T1 right? So I can pull the T1 out if I want to, factor out, and I get a sine 50 here. Plus, what is this sine 25 over cosine 25? Is what? Tangent 25. Okay, so I'm going to write it as tangent 25 to make my life a little easier. And then cosine. Or else you could have left it like this if you want to, and then write it as cosine 50 times sine 25 divided by cosine. Put this in your calculator, get that number, divide both sides by that. Okay. Then come and plug that T1 in here, put these values in the calculator and find that. Understand? That's how you do this. So as I said, I have given a problem somewhat similar to that, but not better worded in a test. So this is again for a test. I'm not going to go through the math. It's algebra. I mean, sorry, arithmetic. This is an important concept as well. Let's work this. This is somewhat similar to what is in the book here. This girl is in an elevator and she's trying to buy a fish. Don't do this, okay, unless the elevator is going on. So what is, she's weighing the fish in an elevator and the elevator is accelerating upward. Now the question is the scale, the fish scale showing the correct weight of the fish or not? That's the question. Think of it like this intuitively. I'm standing in an elevator station. Okay. Now, elevator is going to accelerate upwards. What would my body tend to do?
Go down.
What? This is where Newton's first law comes into play, right? I was stationary. Now elevator is lifting up, but my body will tend to stay where I was, right?
Mhm.
So what am I practically doing? I'm pushing down on the elevator, isn't it? I'm pushing down because I'm trying to stay where I was, but elevator is taking me down. So what if I'm standing on a scale in the elevator? Okay, on a bathroom scale on the elevator. Elevator is now accelerating up. What should the scale show? More than what I weigh. I weigh 140 pounds, let's say, but it's going to show a little bit more. Understand that? That is because I'm pushing down on it, so to speak. Okay. That you can argue it intuitively like that. Now, let's look at the other way around. I'm standing on that fish scale, I mean, on the bathroom scale, on the elevator that's stationary. Now it's accelerating downwards. It's going down. For it to go from stationary to down, for it to go down, it has to have an acceleration, right? Because you change your speed from what? Your velocity from 0 to some value. That means what? What do you have? You have to have acceleration. Remember, acceleration definition was what? Change in delta v over delta t, right? Your initial was 0, your final was some value. Okay? So there is a delta. So for some object that is stationary, for it to start moving, when it starts moving, it has to have acceleration. Okay? So now I was standing stationary on this bathroom scale. It was showing my true weight. Okay. Now it is accelerating downwards. What will happen to my body, you know what I mean, from Newton's first law? I would like to stay where I was. Okay, I don't want to go down. So what is the tendency now for my body to float up, isn't it? What will happen to the scale on that? You know? It will weigh less. Okay, because I'm kind of floating. It's not true, but you can argue it intuitively like that. Yep.
So in that example where you said the elevator was going down, are we looking at the force that's pulling you down, of the elevator going down? We're adding that, or we're subtracting that from the weight.
Yeah,
on the
you
scale?
can handle it like that. Let's work out this problem that will clarify things. So when is the best time to buy the fish? You are weighing something in an elevator.
When you're going down.
When it is going down, right, it's going to show less than what it is. So you are getting a better deal. Do not buy it when it's going. If you want to buy it, be fair, you know, not cheat anybody, then by what? What does that mean?
Still.
Yeah, what else?
Or constant velocity.
Constant velocity, acceleration is safe.
Hmm.
If it is going at constant velocity, then it will show the right. All right, that's what this question is. Here you need to draw the free body diagram and then apply Newton's. So somebody has a fish hanging on a string that is attached to a fish scale. Okay? So measuring the tension on the string. Now it is accelerating downwards, upwards, and then going at some constant velocity. That's the three situation. Can anybody work out part A?
I think so.
1 and 2 things. Shana? We forgot to draw one force, right? That's not completely right there. First thing you draw with the mass is what? The rate acting. You really don't have to draw the top part Q1 down, and when all you're concentrating is mass. Right next to the mass, there's only Q1 up. So that's all you do. What are the forces acting on that side?
Oh, just the one.
No, there are two forces acting on that side. Why don't you write that? Sigma F. There are two forces acting on the object, right? First of all, think about the directions and the signs associated with that. What is your preferred direction?
Down.
Down. What is that 1G direction?
Down.
So that should come in as positive, right?
Yes.
Okay. No. There's no sigma F anymore. We are trying to write for the sigma F. What constitutes it? 1G, and that is only one force, but there is another force, right? That's why I think you're getting confused with these two forces. John, yeah, get rid of that. These are the two forces acting on this.
Okay.
There's a weight acting downwards, tension upwards. There are two forces.
1G minus T1.
Exactly, 1G minus. What is this good for? You can calculate what? How many unknowns are here? Two?
One.
One. Yeah. So find what T1. Oh, what is going on? No, you're not. What did you do? What did you didn't do? So 9.8 times 1 is what? Okay, so why don't you write it first then? I think that might help. Multiply that by 1. You really don't have to worry about a 1, right? When you multiply by 1, you get the same thing, right? Okay, write that next step.
Okay.
So you want to isolate T1 there, right?
Yeah.
What do you do?
Just subtract 1.1.
Then what is left under that side? Negative, okay.
Then just divide. So I just make this negative 3 and plus.
Yeah. So it's going to be 6.81. You don't need a calculator.
She's gone.
What are the units?
I'm not going to.
Only thing I want to see in that is the direction of the acceleration in that diagram. Free body diagram. No, not here. On the free body diagram, what are they saying? 3 meters per second squared up, right? Mark that acceleration. Yep. Next to the weight. Not up there, because you'll never see that. Right, left, or right to the yep. No, it's not horizontal. Just write an arrow here, it's going up, you know what I mean? 3 meters. Okay. Because write that thing there, that way you know the acceleration is upward, so that comes in as positive or negative in this case. This should be negative. Because it's going up. So everything changes, that's the important thing about drawing the arrows with the proper signs, so what do you get now? Yeah, that's 3 should be negative too. This negative should carry on. 12.8. Yeah, because your preferred direction is downwards, right? Therefore, actual tension is what? Actual tension is up, right? Is that right? T1 should be plus, right? Yes. Because this is a negative T1 here, so it should be plus. Have the negative sign. Okay. when it is going up, that is what's happened. The tension is 12.81. Okay, that is why I'm pushing down on the scale, right? Because it's going up. I want us to remain at the same level, so I'm pushing down. So I should have a higher force than other. Make sense? So there are a lot of things to learn here. You know what I mean? Mark your accelerations correctly, the direction. The free body diagram should have the tension and the weight correctly. Then get a preferred direction and go to each vector component and see what the direction is and what the sign there. Yep, question. All right, who can do part B for me? You can do it? All right, just do it. Same thing? Just slightly different. Draw the free body diagram though. I don't want you to do the same thing. You have to draw it here. You need to practice the free body diagram because that if you do not have that right, you can get this question right. What? Are you pulling it down? You know? Okay. What do you call that? MG. What is that? Great. Okay. Good. That is how you draw the free body diagram. The tension, the weight, no matter what, the tension will be always up in this case, whether it is going up or down, doesn't make a difference. Okay? Wrong step. Before here. Decide a sign, direction before even you write the equation. It's up. It's totally up to you. Doesn't make a difference. You can choose it to be up. Somebody else can choose it to be down. The arbitrary direction. Okay. Yeah. Yeah, both are in the same direction, right? Okay. Draw an arrow for that one thing, you know, you just have a line. No, up, yeah, exactly. Okay. So you look at that arrow and look at your preferred direction and then, yes, this is what the equation is. Okay. Okay. That's okay. What? You have a calculator, why don't you use a calculator?
They give you ready for the test? They give you ready for the test on Thursday?
Yeah, because you get a negative at the numerator, you divide by a negative.
I think so. This is 4 point. Well, I don't know about this question, but the question before it was 4.5. So unless it gets a little bit more complicated. Well, it will get more complicated.
Everybody agree with what she did?
Yes. Yeah.
Okay, this is the most important thing. T1 is up. Okay, because that's the end of the string here. Okay, so the T1 will be up. Weight is acting downwards always. It's going down with a 3 meters per second square acceleration. Right here, Newton's second law, she took her preferred direction going down. So come here, this is going down, this is preferred direction is down, so that comes in as positive. This is up, preferred direction is down, so that comes in as negative. And your acceleration is down, preferred direction is down, that 3 comes in as positive. Question?
I think mine probably with the preferred direction being up.
Okay, let me do that preferred direction.
Will my answers be the same or will my answers be the opposite?
Sigma F is equal to MA. Okay, preferred direction up. Okay, now I come to T1. T1 is positive. Why? It is up, this is up. T1. Weight is acting downwards, that's negative. So it's a minus G here. Okay. And the mass is 1. And now acceleration is downwards, but my preferred direction is upwards. So this is a negative. That's the only difference if you were to take the up positive or down positive. That's the only difference.
But my answer will still be exactly the same.
It has to be the same.
So
If you didn't get the answer right, that means you did something wrong in your math.
yeah, I just didn't. I wanted to make sure that I wasn't supposed to get like a negative 6.18 because my preferred direction was the opposite of it.
So let's do this one. T1 comes out to be G, which is 9.81 minus 3, right? This is 6.81. Now I took my preferred direction it to be up, so that will come out to be positive. That means T1 is really in that direction. If I got a negative sign, what does that mean? T1 is downwards. Because I took my upwards to be positive and I'm getting a negative number in that case. Okay, so that means it's really downwards. That's how you do it. Huh? What do you mean? Yeah, so T1 is upwards sign.
But both of those are. That's why.
No, the thing is you drew the sign to be this way. You drew that, you took the direction to be upwards, it comes out positive, that means this is right. You took the direction to be right.
She divided hers by a negative. That's why.
Doesn't make a difference. This is the way you draw this thing is the one that is going to be true. Okay? So she drew it upward and you got a positive number. That means that is really upwards. We took it upwards and we got a positive number. That means what? It's really upwards. Okay? It has nothing to do with whether you select upwards or downwards in your equation. That all depends on the way you draw it. Okay? And the way you drew it and then you got a positive number, that means what? It is really in that direction. You drew it upward and got a negative number, that means what? It should be going down, not upwards. That's how you decide the sign. Make sense?
I got it.
You got it?
Thank you.
So it has nothing to do with what your preferred direction is. It is what you drew initially. Because you really, we knew that, the tension has to be upwards. But if you drew it, you could have taken the tension to be going down, then you'll get a negative sign. What does that mean? That's not really going down, it should be going down. Okay. Say that again? Alright, how do you do question part C? That's the easiest thing. You don't even have to come to the board, right? Amir, what is the answer? It should be G, right? Why is that? Why did you come and do it first?
No acceleration.
Somebody has to do it. Make sure in a test you put the units in there, otherwise I'll say the point of that. 1G is fine, but you have to say it's new. Everybody understand what he did? Sydney, are you okay?
Yeah.
On the right hand side, it becomes 0. Why? It is going at constant speed, velocity of 5 meters per second, right? What does that mean? Acceleration is 0. So your right hand side is 0. When that happens, do not worry about the m and what is a. Just write the 0 there. Don't waste your time. Okay? So then you get the tension is equal heat unit to be F of P, and the F of W is the weight. So tension should be equal to the weight. So that is the same as of if it were just stationary, right? Constant velocity, if it is moving at constant velocity, is the same as of if it was stationary. This is something like what we did before. Okay, two objects, one is 5 kg, the other one is 1 kg. They are connected by a wire and hanging on a frictionless pulley. So one weight is on this side of the pulley, the other weight is on the other side. One is 5 kg, the other one is 1 kg. When you let them go, what's going to happen? 5 kg is going to fall down, 1 kg is going to go up. We worked out a problem, something similar, 5 and 10 or something like that. Just follow. Let's skip that. Okay, now I need to introduce you to friction. Before I go to friction, I want to do one problem, an inclined plane problem. Then we'll introduce friction to that. That's the hardest problem you can get in this section. If you can handle that, I think you're in very good shape. But before I get to that, I want to work out a problem, inclined plane problem without friction. So that will give you practice of two problems of the same kind, one with friction and one without. What I'm talking about is inclined plane is something instead of a horizontal plane, it's going on a ramp like. Keep in mind there are several pitfalls to this problem. A lot of students are getting into trouble here. This is the horizontal surface, it's at an angle like a ramp. And let's say that there's an object sitting on it. Now, let's say that this is just sitting there, and then I'm pulling this thing with the force, let's say 15. So I have a string attached to this thing, I'm pulling that. Okay. You can do this in the lab. How would you do that? You create a ramp like that. How do you create the 50 Newton force? You put a pulley up here, and then on the other side you hang a mass. That will equivalent to what? 50 newtons. Okay? You can calculate that by dividing 50 by 9.81 to know how much mass. Okay? That is how you apply a force to that. Let's say this is a 10 kg mass. Everybody understand now what the situation is? What do you think will happen to this object? It's going to go up on the ramp, or is it going to come down? You really don't know at this point. Okay. So your guess is as good as his guess. You know what I mean? Could be going up, or it could be going down. Okay. All right. So now let's first draw the free body diagram. I'm gonna use a different color and then draw it right there. So wasting my time redrawing it. What is the first thing you ought to draw here? What force? Gravity. Which is in what direction? Yeah, it is. Always gravity is vertically down. I have seen in final exams the gravity is acting perpendicular. That means you didn't understand what gravity is. Okay? Gravity doesn't matter whether it is sitting on a flat table, angle, gravity is always vertically down. Okay? That's the very first thing you draw. That's the most basic force you can So my first force would be downwards. How much would that be? 10 G, right? This G is 9.8. What else? Normal force. What would be the direction of the normal force?
Going.
Vertically up,
Can we just
going down.
can we just do it in components now instead of
That's a bad thing to do.
Oh, okay.
What should be the direction? Remember, normal force comes because of what?
Perpendicular to the.
Perpendicular to the contact surfaces, right? What are the two contact surfaces? One is here, the other one is the inclined plane. So this is the contact surfaces, right? It should be perpendicular to that. So what should that be there? Again, students draw the normal force straight up. That's wrong. It has to be perpendicular to the contact surface. I said this several times already. Okay? And what are the forces actually? Applied force is already I have marked. Okay, 50 newtons is the applied. Frictionless. Okay. First time, let's take baby steps. Frictionless. All right. Now the question would be what are these angles? Remember that this motion can be what? Either going up on the ramp or going down on the ramp, right? That's the only possibility. It can be flying out or it can be crashing in, right, on the ramp. So it has to either slide up, go up or slide down. The direction of the motion is along the ramp. Okay. Now this guy is along that direction, which is a good thing, right? We like things that are along the motion or perpendicular to the motion. This guy is perpendicular to the motion. That's a good thing. What is the guy that is not good here? Gravity. That's at an angle here. It's neither in the direction of the motion nor perpendicular. Understand that? This is the odd guy. It was like the lawnmower that I was pushing at an angle. Remember that? It was trying to go horizontally, but I was pushing it at an angle. What did I do to that force? I resolved that to a horizontal and a vertical. Right? You have to do the same thing. To do that, what do you need to know? You need to know the angle of it. Right? Okay, if this is theta degrees, what would this be? 90 minus theta. Why? If I were to extend this out, this will be a 90-degree angle, right? This is horizontal, this is vertical. This will be 90 minus theta. So if I were to draw perpendicular to this surface here, now do you see that this angle, this will be a 90 degree, right? Because I drew a perpendicular to that. What would be this angle here? Let me mark this one. This will be 90 minus theta. What would be this angle? Theta, isn't it? You see that? Okay, so from this triangle, I get this to be 90 minus theta. Then what I drew was the perpendicular to this inclined plane, right? That means this inclined plane and this line should be 90 degrees to each other. But this guy is 90 minus theta, then this should be what? Theta. So that it should be for addition of those should be 90 degrees, right? So that is clear. So every time you have an inclined plane problem, what you can do is draw a perpendicular to it and draw the weight and mark that angle as the inclined. You see that? This inclined plane angle is the same as of the weight and the perpendicular to the incline. Make sense? Now, what did I say? I said I don't like this weight part, right? It is at an angle. It is neither in the direction of the motion nor perpendicular. What do I need to do now? I need to resolve that to a component along the inclined plane and one component perpendicular. Okay? This is the weight that is acting. I want to get this component and I want to get this. What will be this component here? Along the inclined plane. I have this weight here. Okay. I want to get this one. What do I have to do? Now look at this angle here. This is the angle theta. What am I doing to that angle to get this one?
Cosine.
I'm stretching that, right? So what should this component do?
Cosine of.
Stretching is cosine? No. Stretching is sine. Okay. So I have this angle here. I'm trying to find this point here. Or else let's start with this one. I have this angle. I'm trying to find this component. What am I doing to this angle here? I'm crushing that angle, right? So what should that component be? mg cosine theta. Okay. What am I doing to that angle to find this one? I'm stretching that angle theta, right? What should I get here? mg sine. That is what I mentioned when I was introducing that stretching and crushing business comes handy when you have a situation like this. A lot of students mark those components wrong because they cannot really understand what is contributing to what. All right, I'm going to mark just those two components here. So there will be one component in this direction, and then there will be one component in this one. Very important to get the arrows right, because this is acting downwards. This component will be pointing this way. This component will be pointing this way. You see that? In place of this guy, I have now two components. So this one will be what? 10 g cosine theta. This will be what? 10 g sine theta. Let's make this theta to be 30. If this is 30 degrees, how much would this angle be? How much would this angle be if this is 30?
60.
60. If this is 60, how much would this angle be? 30. That is how the same angle comes up. Okay? And then theta would be 30 degrees here, and this would be 30. Now this guy is gone. In place of that, I have this two.
Okay. So just when you were talking about the components,
Yep.
I guess I got a little lost. But you were saying that if you took that 30 degree.
I have a force here. F. This is angle theta. What is this component? What is this component?
Okay. What did you ask me now? If I have that angle.
This is theta. Okay. What is this component?
That's my cosine.
I have the force here. I'm trying to get this one. I'm crushing that angle, right? So I have F cosine theta. I have this force. I'm stretching that angle to get this one. So it will be F sine theta. I do the same thing. All what I have done is I have turned that thing around here. I have this is one end. This is the other end. So it's X and the Y axis. I have this force acting here. I'm trying to find this component. What am I doing to this angle here? I'm crushing that angle to get this component. I'm stretching that angle to get this component, just like the same spirit of that.
Okay, and so my.
What? This one negative? No, I have already marked the direction going down. That will be negative if I take the positive to be upwards. I have marked the arrow, so I don't have to worry about the negative.
So my question was going to be like with the 30-degree angle that you're given the bigger 30 degrees.
So this is
no, this one on your other.
This is 30 degrees. If you turn this thing all the way around, that means so it will be something like this. That's all. I have that angle. I'm trying to find this one. All what I'm doing is I'm crushing that 30 degrees. I'm stretching that.
I was wondering if that 30-degree angle right there, that you have right there, if you were to just look at that and then take the one closest to your hand, the 30-degree angle, yeah, right there.
Yeah.
If you were to take that and just say take the cosine of that.
Take the cosine 60 if you like.
Okay.
And you're crushing the 60 degree in that case.
Okay.
Because sine 30 is the same as cosine 60.
Okay.
They're the same. Alright, so now this 10G, which was at an odd angle, is gone. What do I have in place of that? I have 10G sine 30 along the inclined plane. I have a 10G cosine 30 perpendicular. That's what I want. Okay? The painful guy, I got rid of it by eliminating. Now, this is, now your life is easy. Make sure you get the directions right. Make sure you get the values right. The angle.
Can you explain the concept of like it's a good mnemonic to remember stretching is sine, crushing is cosine, but why is it?
Because it's upside down, it looks kind of weird, but.
Yes. Okay. This is theta here. Okay. Let's get rid of all the other lines. I have one line here, this is 90 degrees. Okay. I have this 10G, I want to find this component. First of all, this arrow is pointing downwards. When I go here, it is pointing this way, right?
Mhm.
This arrow is pointing downwards. When I go here, it is pointed this way.
Mhm.
First thing to do is to get the direction.
Mhm.
Now, when I go from here to here, what am I doing to this theta degrees?
Crushing.
Crushing. Do you see that? I'm crushing that. So this will be what? Tan G cosine theta.
But why? Is it, or maybe I just don't understand why. If the origin.
It's always been
Like,
back.
it's 'cause
It's always been cosine when it's cosine.
Crushing is always
Oh,
cosine.
is that how it is even when it, okay, when
Okay.
it's normal?
Yes, crushing is all, as long as their two directions are 90 degrees to each other,
Okay.
if there's a force in between, you
Cosine
could look at it from this point of view.
Cosine
Let's call
equals
this alpha, okay? This is alpha. So I have Ng, when I find this one, what should that be related to alpha? What am I doing to alpha angle when I try to find this component? I'm stretching that, isn't it? So what should this be then? Tan G sine alpha. It's the same as
Oh,
tan G cosine theta.
Okay.
You pick whatever the angle you like and see what is happening to it. Okay? You don't have to stick to this theta. You can very well work with alpha.
Okay.
But tan G cosine theta is the same as tan G sine alpha. If you were to draw the triangles and figure out, a lot of students get lost with that. That's why I said that stretching and crushing thing helps in this situation a lot. You understand? All right. Now what I have is I'm going to simplify this. Clean this out. I have this block here. I'm only interested in the block. I can care less about the inclined plane now. I have a normal force in this direction, F of n. I do not know that. I have a component of the weight in this direction. I have a component of the weight in this direction. I have the applied force here, which is Fa, that is 50 newtons. How much is this guy? That is 10 G cosine 30. This is 10 G sine. Sine 30 is 1/2. This is going to be 5 G. And somebody tell me what is this? Is multiply this by G and tell me what it is. 5G, how much is that? 5 times 9.8. 49.05. Okay, how much is this guy? 8.66? Can be.
No, sorry.
Huh? 85? Yeah. 85? Okay. Maybe I should have a calculator class. Okay. So you have the 85 newtons in that direction, 49.05 in this direction. Everybody understand? Only thing that I do not know is what now? F of n. I do not know that. That's all. Everything else I know. Okay? Now, how do I find my F of n? That will be one of the questions. That could be one of the questions here. What is your normal force? Okay? How do I find that? What did I say? The motion is in what direction? Along the inclined plane, right? Is it going up or down on the inclined plane? Is it going up or down? No. What's the acceleration in this direction? Zero. There is no acceleration in this direction. You could have acceleration in downwards or upwards. Maybe you do not know. Let's say that there's an acceleration downwards. A. I mark my acceleration downwards. If my A comes out to be positive, what does that tell me? Actually, it is acceleration is down. Okay? If my A comes out to be negative, what does that tell me?
it's being pulled up.
Although I marked it this way, actual acceleration is up. That's how you figure it. Okay? Question?
Last question. So let's say we
No,
had,
don't make it last. Ask many questions as you like.
let's say we had examined as the normal force sine theta. Would we have had to break 50 newtons into components?
Then you have to, exactly, you have to resolve that. You have to resolve this guy, you have to resolve this guy. That's a painful thing. Nothing wrong with what your method is, what you suggested. But you understand that you have to deal with two forces at this time. That's a lot more painful than getting one force. Okay. All right. Now I noticed one thing. There's no motion perpendicular to the inclined plane. It's either sliding down or sliding up. Okay. So therefore, I can say there is no acceleration in the perpendicular direction. Understand? Just like the book was sliding on the horizontal table, there was no motion in this direction, so there was acceleration. Understand? All right. So therefore, I'm going to use that property. I'm going to say my preferred direction is perpendicular to the inclined plane. That means the normal direction. And going up is positive. I'm going to use Newton's second law there. All right. I have only two forces in that direction, right? These two don't count. Why? They are perpendicular to that direction. Remember, any force that is perpendicular to our direction do not contribute any. It is the same as of vertical forces don't contribute to horizontal motion, and horizontal forces don't contribute to vertical. Same thing now, same concept, just tilted, that's all. Okay. So these two forces don't contribute to this motion, these two forces don't contribute to this motion. Alright, that's what I'm using here. I have two forces, that is all I have to worry about is these two guys. I don't have to worry about these two, because they don't contribute anything to that. Okay. And so my Fn is going away from the inclined plane, that is the direction I took it to be my preferred direction. So Fn comes as what? Positive. And then 10t cosine 30 is 85 newtons. That is this direction. My preferred direction is this direction. So that is negative, isn't it? What is my acceleration? 0. So the whole right hand side is 0. What is this good for? Finding Fn. It is the same as of that weight, street sign was hanging from the rope. We found the tension just like that. We can find the normal force using that same. Yeah.
How did you know acceleration 0?
This
not
object
moving.
is not moving in this direction, it's just sliding. If an object is on this table, it is just sliding along this table. There is no acceleration in this. I found that. Now, the next thing would be to find the acceleration of this object. What direction should I worry about? Along the inclined plane, right? There is no motion perpendicular to it, right? So all I had to worry about is along the inclined plane. Okay? Acceleration I do not know. I'm trying to find it. All right. Let me use Newton's second law downwards. Sigma F is equal to m. How many forces do I have to worry about? Two. What are the two forces? This guy and this guy. These do not contribute anything. They are perpendicular. Okay. And this guy is downwards. I took my downward to be positive. Downward along the inclined plane to be positive. That 49.05 comes in as positive or negative. Positive. And then I have the 50 upwards, right? I do not know the acceleration. I'm trying to find. That's not 0 though, okay? That might not be 0. It could be 0 because it's moving that direction. Okay? So mass is going to be what? 10 kg, right? And acceleration. These numbers come out to be awfully close, but let's say this is 1 on this side, or what to go to then A is equal to what? This is a negative 1, right? Negative 1 over 2. So that means negative 0.1 meters per second. Follow the math here? What does that mean? I drew the arrow going down, but that value came out to be negative. What does that mean? It's really accelerating upwards. Make sense? This is an easier problem than what I can give you on a test, so make sure you understand this. Huh?
Is it easier problem?
Oh yes, the other ones can be with friction and somebody's pushing it at a horizontal and all that. Life can be lots of complicated. There are many things we learned here, how to get rid of the weight that is acting vertically, you resolve it to a perpendicular component and along the inclined plane. And then this is another concept, it's not moving perpendicular to the inclined plane, motion is along the inclined plane, so therefore acceleration is zero. You can find it. Now let's introduce the concept of friction. Not to this problem, let's first start with the
Horizontal surface.
yeah, horizontal. I'm going to use the quick straight away. Why do you think that friction occurs?
It's resistant motion.
Friction is resistance to motion. Why is there resistance to motion?
That's why.
What is there resistance to motion? So friction happens when one object is sliding on top of the other, right? Let's say that you have a box here sliding on a floor, and then there will be friction. Let's say the outer box is going to your right, direction of the frictional force will be opposite to that, the left. Okay? Why is there a frictional force?
If there's like a friction coefficient.
Yeah, where does the frictional coefficient come from? Yeah. Exactly. There is there's two surfaces that are that are touching each other are not smooth enough. There is little bit. If you really look at it under a microscope, it will have some jagged surfaces like that. Then the other box will have things like that. Now, do you see that the one valley will get into the other peak here, and then what do you need? You need to apply a force to get rid of that. To move it out of there, right? That is where the friction occurs. Because the two surfaces, the mating surfaces are not perfectly flat. Okay, they have some imperfection. So this gets kind of tangled by this imperfection. So to get you had to apply extra force to overcome that to move it together. So it is coming from because of the surface imperfection. How can you reduce the friction? Obviously, by looking at that, right, you can come up with a way to do that.
By making the surfaces.
Making the surfaces smoother, right? By different mechanical processes like polishing, okay, and then horning. Like your pistons, you horn. That means that they make it very smooth and so forth. Okay, lapping and so forth. So there are a lot of things you can do, but there is no surface, no matter how much you work on it, there is no surface that is perfectly flat. It's just by the nature of atoms, you know what I mean? There will be one atom here, the next atom here, that means there's a void here, right? So there, when that surface slides on the other, those atoms will get tangled up, so to speak. So no matter what, there will be friction, but it could be very small if you have a very smooth surface, if you polish it very well. What else can you do? That's one way to polish it and make it reduce the roughness of the surface. Yes, you can pump in oil into this nail, right? Then what will happen now? Then this will lift up a little, isn't it? With this floating on the oil inside, right? Between these two. So this will lift up. Now do you see that this is not, too much, forced into this thing, it's floating. So your interaction is less now. This stuff, this was dipped way down. Now it is just touching the top one. So that's why you have lubricants, like engine oil and so forth, to reduce the friction between the surfaces. There are two things that, one of the concept is, let me ask you this question. I have this, let's say this is a nice rectangular piece here. I give this thing horizontally on this table. Okay? And then I try to drag it, there will be some frictional force. That's right. I had to overcome. Okay? Then I give it on this shorter side. Okay? Like this versus this. Okay? This the longer side was touching the table. Now the shorter side is touching the table. Okay? Which one will require more frictional force to overcome?
Longer.
Like this one? How many of you say that this one? How many of you say that this one?
Okay.
2 hands up. No, both are wrong. They are
Both
the
are
same.
equal because of the weight.
Why is that? That's counterintuitive, right? You think that that's the normal thing to say is that this one will have more frictional force because there
Right.
are more interactions, so to speak, right?
So the weight change, the surface weight changes.
No, it's the pressure.
The pressure. Okay.
What is pressure? Pressure is the force divided by area, right? Force here is what? Weight on this, which is constant whether I have it this way or this way, same force. Then this one will have a smaller surface area,
Yeah.
contact area.
That's what I was saying.
So that will have more pressure. What does that mean? This is getting pushed onto the other one a lot harder than the other one, right? When you have it like this, less pressure, start getting pushed. So all of this has more, you know what I mean, more interactions, between the two surfaces. It's not pushed in as much. This one has less interaction, but it's pushed in hard. So they come out to be about. Okay. So what does that tell you? Frictional force does not depend on the contact surface area. Frictional force depends only on what? How smooth the two surfaces. So it's a property of the surfaces only, not the area of the making surface. It depends the property of the two mating surfaces. That's all.
Smoothness.
That means smoothness. Yes, smoothness of it. How smooth. Whether it's a larger surface or a smaller surface doesn't make a difference. All right. So there's another thing that you ought to know is that you have this box, and I apply a very tiny force on this. Okay. What will happen to the box? It won't move, right? Then I keep increasing that force till it won't move. Okay. Then at one stage the box will start moving, right?
Mm-hmm.
So what happened during all that time before it started moving?
You finally overcame the static, whatever coefficient.
Yeah, there was the
So
other
you have to, for this box to move, what should you overcome?
friction.
Frictional force.
Right.
Okay, there is a frictional force opposed to this direction. Remember, when I apply a force, what is the tendency of the box to do?
Resist.
I apply a very tiny force, but even the tiny force, the tendency for it to do is to go to your right, right? Go to my right. But it doesn't go there. Why? There's a frictional force in the opposite direction to the tendency of the motion. Box is not moving, but still there's a tendency for the box to move in that direction, to the right. Therefore, frictional force will, counteract that by acting in the opposite direction. Okay. Then I increased it a little bit more, but still it didn't move. Why is that?
Friction was too much.
Because frictional force caught up to the applied force. Okay. So what does that tell you? Frictional force will keep on increasing till it cannot increase anymore. Then what happens? If I increase the applied force, now it will start. Okay. So keep in mind, frictional force is not a constant value. It will start from zero. If you are not applying any force, there is no friction. There's no tendency for the box to move to the right or left, right?
Mm-hmm.
Just sitting. Only forces acting on that, even though it is a rough surface, only two forces acting on this will be what? Weight acting downwards and normal force acting. Those are the only two forces. The moment I started applying a horizontal force, then there will be a frictional force in the opposite direction. And that will keep on catching up to some level. Beyond that level, it cannot increase anymore. Then the box will start moving. Right. Okay? That is this graph. We don't have the time to do this in the lab, but with the other classes, the regular semester classes, they do this. So that is, this is the motion. You have the garbage can here, and you are applying a force here, and then you have the frictional force, equal and opposite to that, okay, opposite to this one. So what will the net force acting in the horizontal direction?
0.
0. So would it move in the horizontal direction? It started from rest. Then if there is no net force acting in that direction, you stay at rest. Okay? And here, now your applied force is a lot bigger than the frictional force. Now it will start moving. What can you say about the mg and this n here? That is the f of n I write. What can you say about these two forces?
They're equal.
They are equal and opposite in direction because there is no acceleration in the vertical direction. It's only moving horizontal. Okay? So there is no acceleration in this direction. That means whatever the force is downward should be equal to the forces upwards. Make sense? Alright. So this is what happens to the frictional force here. This is the frictional force, and then you are applying a force here. This is the applied force F. That is this guy. This is F of F. Okay, that is this guy. This axis is the frictional force. This is the applied force. Now, do you see that it started with a 0? If you didn't have a horizontal force, there is no friction. Okay, and now you keep increasing this horizontal force, then frictional force will catch up to that. It will from here to here. Frictional force is equal to whatever the applied force that you apply. Okay. After that point, it cannot go anymore. It cannot increase anymore. Frictional force has reached the maximum. Then what will happen is it will start sliding. Moment it starts sliding, your frictional force drops down. Now it will remain at this level as long as this is moving. So this region is called the kinetic region because the object is moving from here to here. It's called the static region. The object is not moving. Make sense? Okay, this is the static frictional region. This is the kinetic friction. So keep in mind the kinetic friction is less than the maximum of static. Okay? Maximum of static region is at here. Kinetic region, when it starts moving, the frictional force drops down. We will be analyzing most of it in this region, kinetic region, that is, this law is applied. Let me write that law, frictional. So, in this one, I have the mg acting downwards here, and f of n acting upwards here, and then this is f of a, that's the applied force, and this is the friction. This is the free body diagram for this. Okay. Now let's say that f of a is larger than f of f maximum. That means what? There's a net force to the right, so it starts sliding. When that happens, you can write f of f. This is the frictional force. This is equal to mu sub k times f. Very important. This is how you model your frictional force every single time. Okay. What do you have to know? You have to know two things. What are the two things you want to know? Normal force. First thing is normal force. You have to know what your normal force is. How do you find your normal force? Usually doing Newton's second law in this direction. You have the normal force direction. Okay. In this case, it will be vertically up. So in this case, the object is not going up or down, it's just sliding in the horizontal direction. So what's the acceleration in this direction? 0. What should happen then? F of n, the magnitude of this should be equal to mg. Okay? We talked about that. So f of n for this situation would be mg magnitude wise. Okay? And mu sub k is for the kinematic, or some books will call it kinetic frictional coefficient. Kinetic frictional coefficient means when the object is moving, that this is a constant. This is a property between the two mating surfaces. Okay?
What is that symbol called again?
Kinetic or kinematic.
No.
Mu sub k, you mean?
What'd you say?
Mu.
Mu.
Mu is the Greek letter for m. Right? Yeah. Mu. U with a longer tail. Okay, so now that's the coefficient of kinetic friction. That's why I put a K here because that could be a static frictional coefficient as well. Okay, that is when it is before moving, the static frictional coefficient comes into play. When it is moving, kinetic or kinematic frictional coefficient. All right, let's look at a few things and then let's take a break here. This is the chart for frictional coefficient. This is mu sub S here, that is the static frictional coefficient. This is the mu sub K. Look at these values. Most of them, the mu sub S is larger than mu sub K. You remember that maximum static frictional force was higher. Moment it started moving, it dropped down. That's why these coefficients are different. Okay.
Except for wax wood.
Say that again.
Except for what does the dash mean for wax wood?
It could be
No. Dash wood.
This one here?
Wax wood, yeah.
That is, it doesn't have a static thing. You know what I mean?
Okay.
It will start moving almost immediately. That's what you can see. Even the kinetic value is very low, right?
Mm-hmm.
Hardly any friction. That's the meaning of this.
Mm-hmm.
And so if you look at it, there are a couple of things. So this mu sub K and mu sub S, you really don't have to worry about mu sub S for this class. We'll be mainly working with mu sub K. In that case, you can see that it's a property of what? The two types of material that are sliding on each other, right?
Okay.
Steel on steel, or aluminum on steel, or copper on steel, or whatever. You don't care about the size of it or anything like that. It's all you need to know is the material. Okay. That's all. And one thing here is what has the smallest mu sub K value? What is the synovial joint in humans means? Your elbow and your knee, right?
No.
Okay. That has the lowest kinematic friction. Human beings cannot get even close. The closest they can get is somewhere here. I mean, this is not a human being's name. This is natural again. Teflon on Teflon is the lowest frictional coefficient human beings have invented. So you can see the nature of it in aluminum.
Okay.
So if you believe in a supreme power, you can appreciate it. Either God or Allah, if you believe. So these frictional coefficient comes in from synovial.
It's not even ice.
Huh?
Said not even ice has.
Not even ice on ice
has less.
That is an order of magnitude different.
Wow.
Just imagine, it's mind-boggling.
I mean, you think about like how you slip on ice. I mean,
yeah, you think
slip.
There's hardly any friction. Yes. Yeah, there's a story that goes with that ice on ice. As you know, I did my PhD in Arizona, so one of my friends flew into Arizona, and then she said, I want to go see the Grand Canyon. It was November, so kind of cold. So I said, okay, let's go. And on the middle of our journey, when we got close to Flagstaff, it started snowing. I even prepared. I had chains on in my car. So what I did was I pulled to a side of the road, started putting the chains on the tires. Then I did two mistakes. I pulled to it was a curve like this. I pulled to this side of the road.
You're on ice.
The other side.
You're on ice.
There was this young kids, a couple of young kids in a car came and take the turn. They came too fast. And now I was putting the chains on the side where I was exposed to the road, and this car was coming in. He lost control. All what I saw was this guy sliding towards me. I'm getting crushed between my car and this car. I didn't even have time to get up and run. All what I did is I pushed that car. That's all I could do. And the car ended up on the other side of the ditch. I felt like the Superman.
Well, I got
So
a.
you can imagine how little force it takes for the car to go all the way across the street on a snowy, you know what I mean? It doesn't
Ah,
take much. So
okay.
that is proof that the
Well, so that defies physics.
Yes. That's the lesson I learned. All right, let's take a break and come back 10 minutes after. So 22 after.
Huh. It's an
Yeah.
incredible story. You were meant to survive.
Yeah.
So, for the break, I know you're already annoyed by this. I mean, I get it. I understand what you're saying, but you still have to have control of rap because I have my own like math thing. So we have this, you know,
Yeah.
and then we have there.
Yeah.
And then it's over here. Oh, good. Yeah. But it's still long term.
This angle is 90 degrees. So this plus this should be 90.
Okay.
How would this be? I mean, how would that be? If it is already 90 minus theta, this is theta. So then you add the two.
So you were saying that if you took, you were saying if you crush this angle,
Yeah, if you want to get this component,
yeah, you want to get this component, then we're already given.
we have this force acting down. We are trying to get this component.
So you're saying we want that. We want to get this. So you're saying if I take 5 cosine
Yep.
theta, right?
Yep.
And I guess I was looking at it as thinking, if you gave it to me, you said,
Yeah.
and you said 7, this would be 16.
60 on the other end.
Yeah. So I was putting my calculator. I was like, okay, this is 5 right here. This is my hypothesis. Okay. Right? I was thinking,
You can do the
if
same.
I was thinking, it should come out the same, but I was getting a different number, and I was wondering why. Because you would have done to get this, you would have done the crush. You said 5 sine, and then that this angle.
Yeah.
Right. Theta. So that's
Or else, if you want to take this angle, now you're crushing what angle?
60, right?
Same
I
thing
tried.
as a cosine 60. Then this will be sine 60.
So I was wondering why I divided that. Because I did.
That is because now when you get the 5, it is not from here to here, it is straight down. You have to drop a perpendicular from here. That's the hardest.
This is still 9 degrees.
It is 90 degrees, but 5 doesn't stop there.
Oh,
5
5 kept going?
That is why when you try to do it, then I mean, trick, it is so confusing what is
Okay.
what. you know.
Right, okay.
That's why I keep saying that doing the crushing and
Okay,
splitting
'cause,
thing,
yeah, I
it's
was
a lot easier if you get the hang of it.
I was sitting there confused, like,
Yeah.
this should come out.
Yeah. That is because the 5 doesn't stop here. You know what I mean?
Right, okay,
It is-
alright.
This is not the opposite side of that right.
Alright. Yeah, definitely.
We're doing about homework how you have to find the range and the angle. It
Yeah.
doesn't give you anything.
What have they given?
Nothing.
Oh, nothing. Then we can find.
Well, how are we supposed to answer the question?
So what is the question?
It's like,
It should be related to the book.
oh,
These questions are at least
Are in the
related
book,
to the book. Numbers could be slightly different, but
it might be in this stuff going set.
4, that is from chapter 8. Read through this and tell me. Should be for you. Might not be
I
additional.
did most of these, and I didn't see.
That's related to the last. So it should be somewhere.
Oh, see, I did this wrong. Once you find the angle and the range max,
range maximum will be when it is 45 degrees, right? If it is surface tunnel.
So does that mean the angle's 45 degrees? Are you serious?
We talked about that.
Yeah, like when we first started. Oh my goodness.
So that is a hidden thing that, you know what I mean, that's not written out, spelled out for you, but you need to.
So then, how do you find the range max after the you know the angle's 45 degrees? You have to use the formula.
You take, now you know the angles, you take the vertical component, horizontal component,
The cosine of
cosine of whatever the V, cosine 45, V sine 45 will give you the vertical. Make your table and then use the table. I wish you had the question, we could put this.
I can pull it up.
Are you there yet? It's wrong.
Let me see. So this is the.
Oh, no, maximum height of its flight is equal to its horizontal range.
See, I think I did. This is how you would draw. I think this is how you would draw it right
Yeah.
here.
No. This is not saying you have the maximum horizontal range. So it is. This is R. This is also R. That's all it's doing.
Oh, yeah, they're saying the maximum range is the same as
As
the
no,
height.
maximum height is the same as the horizontal. It's not saying it has a maximum range.
Oh, they're just saying that they're the same.
They are the same, so it could be any angle. Only when they say horizontal range is maximum, then you know the angle. Here the angle is not.
Okay. Yes, because they want us to
Find the angle exactly.
How do you? Oh, you want me to draw it out?
Yeah.
Well, it's thrown upward.
Yeah. So take it to be
From the
theta.
ground,
Take
okay.
initial velocity to
This
be
is the ground, right?
Yep. Initial
The
velocity.
ball is going from here, right?
Yep.
To here.
Yep.
Okay.
So this from here to here is R, right? That's the range.
The range.
Yeah.
The range.
And then the height is also
That's the range.
range is actually then maximum height is also R.
This is
That this.
Yeah.
Okay, that's what it is.
yes.
Alright, now take your initial velocity to be this. You have your horizontal component.
Horizontal is going like this. You mean I should do
Based on these values, what is that?
I should do it like this?
Yes,
So
initial. Remember what we write initial, right? Yeah, VI. Which is the
0. We're going to x right at 0. Wait, what do you don't know it.
yeah, so you write it in terms of V and Z.
Oh, okay. So you want me to do it like
Brushing and
maybe
exactly. Is it positive or negative? Is in this direction? Mark it. That's fine. Yeah. What is this come?
This y is going this way.
Yeah.
That's going to be sine. And that's going to be
Yeah. That's okay. Now, do the motion from here to this point. To the highest point.
from this.
To there. What is special about this point?
Oh, that's the final one.
Yeah. Yep. How much is that?
It's going to be the same as this.
Good. It never changes. Just put, yeah.
I can do that, right?
Yep. What is the white one?
0.
Good. Okay. What else do you need?
What is the completed?
Delta X there.
Acceleration.
Yep. No, no. Delta X will have a X and a Y. Two different ones. For this one, it will be horizontal, and then this one will be up.
But why don't you want me to draw the arrows?
No, draw the arrow. There's no delta X. This is delta X. That's the displacement. For this one, for the X, you get horizontal. Actually, you should have these arrows inside. For the X.
When they have it in
Exactly. You see that the visa phi is up here, this is horizontal, this is up here. Those are the differences. X's is can be horizontal, Y is up. Don't have it out here. This is just
draw it first.
no. This is just to say this is we are talking about
So
initial
this-
velocity.
You say this is what it is.
Exactly. That's the
Yeah.
that's the one that we are talking about. Then we look at the arrows. Okay. Delta X. What is that?
Oh yeah, okay, I get what you're saying.
Yeah. Horizontal. How much is that? No, no, you know something about that.
Oh no, we're gonna they said it's this is the range.
Yes. So you are going only from here to here. So
It's
what
gonna
is
be half of that.
half of that? So right there.
Oh, so you write 1/2 R.
Exactly.
Oh, okay.
What is this guy here? What's the direction in the first place?
This is what
Yes. Up. Okay. How much is that?
it's gonna be this.
Yeah.
So we're gonna use it's gonna be R.
Not 1/2. 1/2 is the total thing. We are just considering from here to here. We are not
So
considering
then the
from
x-axis is this. 1/2.
exactly. But why it is
R is just R.
exactly. What is A?
And you don't consider it to be 0, right? You don't
No,
assume that
no,
it's 0. Only
Yes.
only when it's done vertically up, right?
Vertically up. Yeah, vertically up and the very
That's
top.
how we did in the first one. That's when we find it's going to be on the y-axis.
Yes.
Alright, so we have acceleration.
Yeah.
Acceleration is x-axis. 0.
Good.
Acceleration y-axis.
Yep.
Or either positive.
That's
or
it. It
negative.
doesn't matter, yeah. No,
Doesn't matter if it's
no.
negative.
If you put the arrow down, it's not negative.
Well, these are positive.
That you don't care. You write the arrow properly for this one and mark the sign. Isn't the acceleration due to gravity is downwards, right? So that should be good.
I thought this was negative.
Because acceleration is always downwards, it's not up. So this is always downwards.
Positive?
Downwards. Okay.
Alright.
Now
Now I can use my equation.
kinematic equation, then fine. There are two unknowns you have, VI and theta, you can find. They will come in terms of. Try that
And then how do I do the R?
Try that and tell me or come and talk to me money or email. Okay? Because I had to get on with the rules. I'm gonna log you off, okay? That was my book.
Oh, no. Oh, yeah. Do you guys use the same book for the second one? Physics 2?
No, this has, yeah, this, if you buy the whole thing, it is physics 2, it's also.
1 and 2, right? For
Yeah.
this book, right? And it's good for like a year, right?
Yeah, 2 semesters.
2 semesters. The summer count? No, right?
Now, whenever you take physics 104, you use the same book.
Same book, right? Yeah. I need to. I don't want to do that.
All right, now.
That's how I did it.
Let's do this problem. This is an easy, I mean, basic problem introducing you to friction. Yeah? 200 gram steel box rest on steel floor. What is that information good for?
To find the coefficient.
Find the coefficient, frictional coefficient. Okay, steel on steel. So you go to the textbook, look it up, steel on steel. What is your mu sub k? Okay, what is the minimum force required to move it at a constant speed? Okay, now it is moving at a constant speed. So what frictional coefficient comes into play here? Kinematic frictional coefficient. So you need to go to the book and look it up. What mu sub k is for steel on steel. Steel on steel mu sub k is 0.57. Okay, note this thing down. Steel on steel is 0.57. You have to use that information to look. What is the other thing that you need to pay attention to? Constant speed. That means what is the acceleration? Zero. Okay. So in that case, what is happening now? When the accelerate constant speed, that means what? The net force. What can you say about the net force? Net force is zero. There is no net force. That's why it is at constant speed. And then for the net force to be zero, what should happen? All the forces should cancel out, right? Equal out. Whatever the forces to your right should be equal to the forces to your left. Okay. Then draw a free body diagram. Draw a sketch first, and then draw a free body diagram. One other thing you need to worry about is what from the given data. Conversion. Why it's 200 grams? You need to convert that into kilo. Make sure you do the rest. So they're asking for a minimum force. That means what? It's applied force, right? FA. That's what they ask. Let's say that you are pulling it to your right. What is the direction of the frictional force? To your left. Okay. When there is a frictional force involved, if they haven't given you the frictional force, you will have to always use that f of f is equal to mu sub k times f of n. That's how you figure out the frictional. Who can work this out for me? One hand up. Two hands up. Mandeep. Doesn't write that well, right? There should be half arrow on top of it. Why is she worrying about an f of n?
Which end?
To calculate f of f.
Oh, yeah, 0.2. You feel very box.
200.
Oh, sorry.
I'm curious. The 0.2 is supposed to be multiplied times 9.81, right? To get the newtons, right? I mean, I'm just saying, like, yeah. I mean,
Oh, to get the newtons, it would be the mass times, yeah, the acceleration.
okay, where is she getting the? All right, okay, yeah, you say you didn't work it, so it's cool.
Very dangerous. Writing things without writing an equation, directions, nothing. What did you do there? You applied Newton's second law, right? You have to write a direction and write the equation before you do it. Do not write that directly. You did well for that part. You had narrow up sigma f is equal to ma. Here you just jumped into the equation. No, on top of that, right there. What direction? On top. Write the equation. What direction are you using? Isn't this the same thing that you're applying here? Okay, why don't you select a direction, write the equation, and then apply it? You bypass that here. Exactly, that's what I said.
What the heck would you say it can work?
How much is f of n? Oh, you already calculated. Yeah.
You say Fn is
Yes, these topics, maybe I'll start energy, but yes. All right. Everybody agree with what she did? Did you get the same answer? You did?
no.
No?
I want to say us.
What was wrong?
No, I didn't say she was
Is
wrong.
this right? Frictional force? Yeah.
She rounded. She rounded.
Oh, you mean right here? Oh, okay, that's it. In the test, don't round it, go to the very end and then look at this expression.
It was 1.962.
Yeah, something like that. By the minor number. You know the rest of it. If you didn't round it, you can.
All right.
Alright, so the important thing is here there's no acceleration in the vertical direction, there is no acceleration in the horizontal direction. Why? Going at constant speed. Okay? So
Okay.
actually it should say constant velocity. But this part becomes zero here. So Fa is the applied force and the frictional force. That's the important thing. You need to calculate the frictional force is in this direction.
That's actually 1.14.
What is that
It should
number
be
down there?
1.14, not 1.4.
1.14, right?
Jesus Christ.
All right.
Can I ask you a question?
I got 1.1.
Professor Sinkin? Professor.
1.1? 1.12? That's okay. It all depends on the round. Yeah.
Where did she get the? Is that point? Was that where did she get the muse k from?
Where Where did she get what?
How did she get her figure for Muse K? Muse sub K.
Muse of K.
Up top.
She looked up the
Up. Oh, okay.
textbook,
Oh, okay. Okay.
steel on steel,
Gotcha. Now,
0.57.
okay.
I showed that on the
Yeah.
board.
Gotcha.
Should we memorize this for the exam?
Oh, you had to memorize the frictional coefficients too. No, no, come on.
Ah. I was like, what?
I will give you the relationship f of f is equal to mu of k times f of n. That will be part of the equations, and sigma f is equal to ma will be part of the equations. It's already released, I think. I released the equations.
Will you give us,
Yeah, I'll give you the frictional coefficient. I might give you a chart and ask you to pick that, but still all the information. All right, let's do this one here.
Huh? Yeah. 301. 661. 4992. Air. Young. Yeah. What's your name? Okay. My phone's dead right now.
Okay, it's okay.
This question introduces you to another concept. When the brakes are locked,
0.
that means you are skidding.
The acceleration is 0. Oh,
No, doesn't have to be.
yeah.
But remember, this is a lot of students misunderstand this one. Your brakes are locked, that means you're skidding. In that situation, what kind of frictional coefficient applies? Is it kinetic or static?
It's kinetic.
It is stated there, it's kinetic
Oh,
friction.
I knew.
Okay? And when the brakes are not locked, that means the wheels are rolling now instead of skidding. That is static frictional coefficient. Okay. What is the significance of the two? Static frictional, when the static frictional coefficient applies, your frictional force can be very high. Because remember that it goes up and then drops down when it's kinetic friction. So when you're skidding, you have kinetic frictional coefficient and therefore frictional force is less. Okay. So what does that do? It doesn't hinder your skidding, right? You can skid for a longer time. What do you want to do? You want to get the static frictional coefficient going instead of the kinetic friction, right? How do you do that? By turning the wheels towards the skid. Then what will happen now? Now your wheels might start turning, and then moment it starts turning instead of the skidding, what kind of frictional coefficient comes into play? Static frictional force. Then you have a higher frictional force. It will come to a stop a lot sooner than if it were to stop. That's why they say in a skid to turn the wheels towards the skid. that you want to get this wheels to turn instead of spin.
Okay.
So this is what dry concrete, right? So you'll have to look at the dry concrete kinematic friction. Rubber on concrete, so it is 0.8, right? The kinetic frictional coefficient is 0.8, right?
Mm-hmm. Mm-hmm.
Static plus 1. So that is the highest frictional coefficient you can have. And that's why roads are made of concrete, or at least asphalt, which is pretty close to concrete. And you have rubber on your tires, not the steel. Because that will give you the most static frictional coefficient. Who can work this out? You had a question? Who can work part A? Yeah, this. Okay. Then how to do part A? Now what they're asking is what distance will this car skip? Starting at 60 kilometers per hour. But what is this good for? You found the frictional force. What is this frictional force good for? Actually, there is no applied force. You know, I mean, the car is skidding. You know what I mean? So there's no applied force. Okay. So the car is skidding, and now it's coming to a stop because of the frictional force acting opposite. Okay. Now you're starting with a 60 kilometers per hour. What is your final velocity? Zero. Now you can use the kinematic equations. Not actually, you have to use the Newton's second law to find the acceleration, right?
With this or with this?
Normal force, there's no motion in the vertical direction. It's all sliding horizontally, right? Should have been that. Okay.
Can I ask you why didn't you're fine. Why when we were going with her diagram, I forgot what we call it already. Why wasn't there a force for the 60 acceleration or the going in whatever direction it was going in?
Yeah, actually, it's not really clearly written here. Assume that the engine is turned off, car is skidding.
Oh,
When it reaches 60, or put it in neutral or whatever.
okay.
Others, they'll have to specify what force is acting on it and all.
Okay.
Yeah, looks okay. Did anybody else get the same answer? 17.70 meters. Huh? 17.8. That's okay. Yeah. All right. Does it make sense?
Yeah.
Why is it? Because although the car slide in this way, so a frictional force is acting this way, so your displacement has to be to your right, right? Your right leg.
Yeah.
Well, yeah, that's the only thing that kind of like I'm fuzzy about is that there's a frictional force,
Yeah.
there's the normal force, there's a weight,
Yep.
but the car is moving in another direction. So what force is that? I mean, where's the arrow for that?
So the arrow for this should be this. You start with some velocity and there's an opposing force, so eventually it's going to come to a stop. That's what happened to the car. Car is moving at 60 kilometers per hour and then, it is skidding.
It's moving. It's moving. Why isn't there an arrow for? Yeah, I'm kind of lost on that. It's moving, so where's the arrow? I mean, in the diagram, where's the?
Velocity, yeah, it is moving with this velocity to your right.
Okay.
But the frictional force is opposing to that motion, so eventually it's going to come to a stop.
And then my question would have been, how does that factor in when she was doing her equation with the friction? It's not drawn there, but it's understood, and it's not.
The direction of the initial velocity comes in kinematically. In the Newton's second law, there are no velocities involved. It's just acceleration, mass, and the force. Everybody understands? Do I need to explain what she did here? The normal force is upwards, weight is acting downwards. It is not very clear here. What happens is when the car is 60 kilometers per hour speed, engine is cut off or it's put on neutral. So the car is sliding now with that initial speed. That's why there is no applied force here. Okay.
Mm-hmm.
There is no applied force here. Only force that is acting horizontally is the friction.
Okay. So typically we want to use our frictional force to find our acceleration. In this case, okay.
Only force that is acting to bring it to a stop is the friction. So it's moving in this direction, but the force is applied in the opposite direction. It has to come to eventually a stop.
Okay.
Who can work part B? What's the difference with part B and part A?
Obviously, static versus
Only the
kinetic.
frictional coefficient changes, right? Instead of 0.8, what happens to that? It becomes a 1, right? Static frictional coefficient is 1. So only this one stays the same. So here instead of the 0.8, it becomes a 1, so you get 117772, right? From this here. So you put that in here, and now your acceleration can be larger than a big force. So that means what? You're going to come to a stop sooner because the acceleration is larger. You can come to a stop sooner. That's the whole idea of having static frictional coefficient versus the kinetic friction. You want to get the wheels to roll instead of wheels slide. Okay. Well, how do you answer part C? That's not a very good question. What force did the road exert on the car to stop? It's the frictional force, right? Frictional force is the one that the road exerted on the car for it to bring to a stop.
Yeah.
All right, this is the one. Something like this could be on. This is the hardest question that can be on. Oh, yes. Friction will be on this test every country. It might not be as hard as this one, but if you can handle this question, I think you have fairly well prepared. It's an inclined plane that has friction. Yeah,
The information you were running today, is this the last information that's going to the test? Or, okay. So it was on Monday and Tuesday was not.
Monday and Tuesday I'll be working on something else, energy and work done. I took all those sheets out of that unit too. All you'll be responsible will be two-dimensional motion, that is projectile motion, relative velocity, and Newton's, that's chapter 4, this stuff we are talking about. And then I will give you several vectors, like the quiz that I gave you, like somebody was going at some, 80, 50, kilometers, you had 25 degrees to east, blah, blah, blah. I'll give you some vectors. You'll have to calculate the resultant or the equilibrium.
And then friction.
Friction is this in this chapter.
So this is the rest of chapter 4. Everything we done there.
Yep.
Wow.
It's all here. So in part A, there are no other forces acting. You have an inclined plane that is 25 degrees to the horizontal. A box of 50 kg is sitting on it, and there's no friction. What will happen to the box? It's going to slide down, right? It's going to slide down with some acceleration. And this is another common mistake students do. They mark the acceleration to be 9.81. It's not free fall, it's sliding along an inclined plane. Okay? So that's not true. It's not 9.8. It will be less than 9.8. In part B, you have the frictional coefficient. Now it's coming down at constant speed. Your theta is different.
Part A, we have to set it up like how we.
Exactly. All you have to do is to resolve that weight, which is vertical, to a perpendicular component and along the incline. Then you have all the forces acting on it. Use the Newton's. You have to use the Newton's second law perpendicular to the inclined plane and along the incline. These are standard, methods that you know how you handle this kind of problem. So, think through and then work it out properly. Who can work part A from? 1, 2, 3. You can? How about Krishna? Can you? Part A? No?
And you said G couldn't be 9.81, right? G is not 9.81.
No, G is 9.81.
I thought you said it couldn't be.
No. Acceleration cannot be G. That's what I said. It's less than G. G is 9.81, but the acceleration is not G. That's what I meant.
Okay, that's what I say. How could we figure this out?
Maya, can you work out part A? You can try. Okay, let's do it.
This is just basically like what we discussed. This is basically like what we were discussing earlier.
What is that thing that you draw in that arrow? No, 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 in the diagram. Okay. So before you do anything, you have to do something with this guy. Yeah. Can you draw the two components before you apply the? But draw the line and do this with the line, not this angle. Right? Yeah. Crushing what angle? Yeah. Crushing what angle? You did one thing and you're saying something else. You are crushing what angle are you crushing? 65. Okay, so that's cosine 65. Or else you can look at this guy. What are you doing to that 20? Stretching 25. Or crushing 60. Both are the same. Okay. Where do you get that from? Fn. Fn is totally different direction, right? How can that be equal to the rate acting down? Impossible. What did you find? You got 50 times g, right? What is that called? Okay, what is the symbol for that? In g or weight, right?
Yeah. Right.
Yep, these are components of the force, right? There should be a half arrow on top. How many forces are in that direction? Just one. What is that force? How much is that force? They calculate that force already.
I know.
You guys finish it?
What is that X and Y? What does that mean?
What'd you get? What'd you get?
Okay, that's what I
For
asked.
A. For A.
Is that positive or negative?
4.146 or whatever. What'd you get?
Yeah.
Yeah.
Okay.
Okay.
4.14.582.
Oh yeah. Yeah.
And then
Okay.
it's just 4.1, so it takes two significant figures.
Okay.
So that's what you got?
Yeah. Yeah. Same thing.
With the X and Y on there. Then it would be like it combined and so this is talking about those
constant speed 0.
giving
Then
the signs of the relationship between this and this.
15 degrees.
You're holding it like this.
So
This is the Y, but this is the X. The Y because that's what my evidence is.
is
I just kind of put right. That's exactly.
oh, so it's not.
Okay.
And then
You mark the acceleration.
Calculate.
So you should have marked the A going down. Okay?
yeah, you got the Y.
Okay, that's how it became. So you mark that and it comes out to be positive. So what does that mean? It's really going down with the acceleration. If this was, is that the direction of the acceleration? Is that the direction of the acceleration? That's nothing to do with horizontal and what's the direction of the acceleration? Going this way, so you have to draw it at an angle going down.
I mean, I wouldn't doubt if I did it wrong, so.
Be careful about those things. So it is going faster and faster, sliding down. As it slides down, it gets faster.
So is everybody
All right. Anybody understand what you did?
Yeah.
equals 0, right?
What we got? What we got? What we
So you
got?
got the two components of the weight here. This is weight, MP is this much. But this component to be this and that component to be this. Then she used, it should be at an angle here. So she's using at that direction as positive, going down along the inclined
Yeah.
plane, sigma F is equal to MA. And this component, that's the only force acting in that direction. And that should be equal to times A, she gets a positive value, okay, of A. That means actual acceleration is in that direction.
Yeah. Yeah. The part with the A.
What is your question?
The same thing is just where she went from, where she found her A. I guess from she plugged in.
Because acceleration doesn't move in that direction. That's when she used the X. Not the Y. Yeah.
If there's no motion perpendicular to the inclined plane, you use that if you want to find f of n. In this case, they are not asking anything about f of n. They're asking for the acceleration. It's just sliding down the inclined plane. So using this perpendicular to that inclined plane doesn't help you with that acceleration.
I thought that the sign was the part that's going down.
This is the angle, so this
Sine.
will be sine.
Yeah.
That's right.
Right. That's what I was saying.
Yeah, so that is what this one is.
Okay. So using that, and then
Yeah,
plugging that in.
490.5 times sine 20 probably gave you this. Can somebody calculate that? Yeah. Really?
Yeah. 4 point what?
Because it's going to be 65 degrees. It's not a 25.
Oh, okay. To the horizontal? No,
What?
this is 25, so this should be 25.
Yeah. What number do you
So
have?
this component is nothing other than mg sine 25 here. And this component is mg cosine 25.
Right. Right.
Yeah, how much is this? Can somebody calculate that? Oh, so she got the x and the y mixed up then.
Yeah.
So
Okay.
x and the y is mixed up here.
Okay.
Okay.
The X and the Y mixed up.
Yeah.
So is there a right?
That's why I never write x and y. I write this and then I calculate this.
Yeah,
and
that's what I was
write
thinking.
it
Like,
out.
okay.
It's clear to me along this plane I have this much force perpendicular to that. You know, I don't write x and y. I write mg sine 25, mg cosine 25, then simplify that and write the value.
So the a should be 4 point.
So
Yeah, I'm
it
sorry,
can be
4.1.
this divided by 50. So
Right.
yeah, it's going to be 4.
Okay. Okay.
This value is.
So hold on, that's not right. The acceleration not right.
It should be, this value should be coming. 47.29 is equal to 50.
Yeah. Okay. Okay. So then for part B,
So for the part B, there is a frictional coefficient. You're supposed to calculate what the frictional coefficient is. Now it is sliding down, it's at an angle, different angle.
Right.
15 degrees here.
yeah.
Okay, let's,
So mg is 126 or 127. Calculate yield if the box slides down at a constant speed. And a constant speed means that a is 0.
good.
And so they should be equal
So
to.
this is 15 degrees, so this is going to be 75 here.
So moose should be equal to both. They should be equal. Moose should be equal to 127, right?
Okay, so now there is a frictional force involved here. There's a means of K that's given. So the
Right.
frictional force will be in this direction. F of x.
No, if it was equal, it wouldn't be moving because the net would be 0. Well, okay, I'm listening.
Okay, the other thing they are talking about is sliding at a constant speed, right? That
Right.
means what? What's the acceleration in this direction? Zero, constant speed. Okay, a is equal to 0. Now, before we do anything, we have to first find the moment you are given frictional force, you have to find f of f. Okay?
Right.
Okay, that's how you model your frictional force. F of f is equal to mu times f of n. So you need to find f of n first. Okay? So what I'm going to do is I'm going to use this in this direction, sigma f is equal to m.
So 1.
F of n, that is in this direction, you should put arrows to these guys, otherwise it's meaningless. So this is in this direction, that is positive f of n, and then there is a weight component in this direction, which is going to be mg cosine 15. That is negative.
Oh.
It is in the opposite direction to my preferred direction.
Okay.
Okay? Negative mg cosine 15. M is what?
The mass.
Is,
Yeah.
50, right?
Yeah.
So 50g cosine 50. That's the net force acting in that direction. What is the acceleration in that direction? 0. It's not going anywhere, right? In that direction, it's not moving there. Then in that direction, so that's 0. So this is good for your normal force. That's nothing else than 50g cosine 50.
Gotcha.
How much is this?